Good afternoon, everyone. Am I audible? I hope I am audible to all of you. So, we'll start this session. Welcome back to the fourth session of our faculty development program on Industry 4.0. It's my pleasure to introduce our distinguished speaker for this session, Dr. Ankur Beohar, who will be delivering the talk on future of VLSI digital design, industry insights, and digital twin technology and simulation. Dr. Ankur Beohar is currently serving as an assistant professor at the Vellore Institute of Technology, VIT Bhopal. He holds a PhD in microelectronics from IIT Indore, where his research focuses on performance enhancement of 3D cylindrical gate all around tunnel feeds FETs for ultra low power circuit design. He has a strong academic background with an MTech in VLSI design from Manik NIT Bhopal and BTech in Electronics and Instrumentation from RGPV Bhopal. Dr. Bevar brings with him extensive research and teaching experience across several prestigious institutions. He has worked as a project engineer at Reliance Communications and has served as an assistant professor at Swami Vivekananda College of Science and Technology and Technocrats Institutes of Technology, Indore. He is also contributed to advanced research as a research associate and a senior research associate at IIT Indore and as a postdoctoral fellow at IISER Bhopal, working on projects sponsored by the Council of Scientific and Industrial Research, New Delhi. Dr. Bevar is the recipient of several prestigious fellowships, including the Senior Research Associate Award under the Scientist School Scheme and the Postdoctoral Fellowship in Electrical Engineering and Computer Science from IISER Bhopal. We are truly honored to have him with us today to share his insights on emerging trends in VLSI and the integration of digital twin technology, a topic that perfectly aligns with the evolving vision of Industry 4.0. Let's warmly welcome Dr. Ankur Beohar sir for his expert session on the future of VLSI digital design, industry insights, and digital twin technology and simulation. Sir, the virtual platform is all yours. Over to you, sir. Dr. Ankur sir, over to you. Please continue. All the participants are requested to please mute your mic. If you have any query or doubt, you can type in chat box or at the end of session we'll have Q&A session.
Sir, just a minute. Yeah, thank
Yes
you,
sir,
sir.
yes sir, yes sir.
Sir, not audible, sir.
Wait sir, wait sir.
Yes, sir.
Yes sir, you are
Thank you
audible.
very much. Am I audible, now, sir?
Yes sir, yes sir.
Okay. So first of all, thanks to the Sambhaji sir and my sir and other team members for the opportunity to have an interaction here right now. So let us we start about the basic and some analysis about the future of VLSI digital design industry insights. However, we know that once we start for the digital design, we have should to know about some basic flavors of our VLSI of analog also. So I think it is required for us to discuss some basic VLSI feature, then analog, and then device to circuited how we can approach about the VLSI industry and with the help of some digital product or the digital device implementation. So, sir, is it visible? I mean, the slides here.
Yes, sir. Visible, sir.
Okay, thank you, sir. So, again, I welcome all faculty members and the other staff organizing members. We have an opportunity here. Now continue. So, as we know that for the VLSI, the very basic, we have an implementation started from the small scale, from the very basic. We go for the MSI, the beginning of the 1960s. We have 100 transistors that given to the hundred, to the thousands, and now more we have go towards the lakhs. So once we exceed over the thousand towards lakh in the billions, so over lakh we have started one after that small scale, medium scale, and large scale. We go up directly spilling towards the VLSI. Since the Intel proposed first processor in 1971 as an 8080 by 4004, which has been later on advanced by the 8080 and series like that. So nowadays, the industries which we have going towards ST microelectronics, Cadence, Synopsys, Qualcomm, so on, that will go towards and focus over that VLSI now. So as we know that the transistor revolution from that 1948 at Bell Labs by our famous three scientists of USA, William Shockley,
Right, sir. नको
and
आगे.
Richards, this
था.
posed these scientists that transistor basically converted over the revolution for the VLSI, the basic element right now. The processor, the 4004, we
Network
are
problem.
beginning with the consist of the 1000 transistor with a limited frequency of 1 megahertz operation. However, the feature is limited, frequency limited, but we have proposed and achieved the multi-functionality with the help of processor design. The multi-chip modules we have been understood, where we have the input, output, memory, and the peripheral devices and the controllability over the same unit dice chip that constitute the multi-chip modules and the IC chips. In continuation to follow the Moore's law, we know that the number of the number of component and the transistors increasingly, double in every 18 months or 24 months, or we can say in the number of 2 years. So to follow the Moore's law, we yes, sir. Hello. Any any query? Any? So shall we continue?
Yes, sir. Continue, sir.
Okay,
Yes,
sir.
sir. Please continue.
So we know that the grandfather of our VLSI society and the evolution, that is Moore's, Professor Moore, in 1965, he proposed one idea and predicted one statement that number of transistors, the component will double in every year. And that his prediction later on become the law, that is Moore's law, by the VLSI International Society and the association members, where we found that the number of transistors on the same area. That is why from the huge computer we convert towards the compact desktop. From the desktop we come to the laptop. From the laptop we come to the mini laptops, gadgets, tablets we have, and now we have a very effective and the lightweight right now the technology we have in the form of laptop. Similarly, we have in the form of high features for mobile also. So that compatibility, the area we have remains the same, even the low area, but our feature and the number of components that become the double. So it was the courtesy by the Intel. So, but the problem is that at the same time, when increasing to the lower technology node, now the Intel to work over the less than 9. Nowadays, less than 10 nanometer and now 15 few picking over the 1 nanometer and 2 nanometer for that. So problem is about the power dissipation. When we increase towards the lower technology node, as per the data would be in that 22,000, we have the microprocessor and the power dissipation continues to increase. So in order to control that, so many researchers and we have some technology that we have to propose over it right now. So we have a one abstraction level that in order to work for the memory system or for the digital design system, we have to go from the very basic element that is device. Device means in the form of either MOSFET, FinFET, tunnel FET, graphene FETs, any other device we have taken, and over the after the customized optimized device, we have to go for the circuit implementation. Once the circuit implemented, we will, with the help of model, prescripted from the gate, and from the gate module, we design the module, and finally the abstract of the module for the system, right? So slowly we will see. So as a basic elementary, let me see towards before implementing the digital design circuits, we have to go from the very, I mean, hierarchical flow from the device. Device in the form of like MOSFET, we everyone know the basics of MOSFET that have the terminals, and if the channel length is there, that is more important between the source and channel, source and drain. And if we go towards the lower technology nodes, that means we are basically talking about the lower channel length. Once we go, we will decrease the channel length basically, and may use for switching and other purposes also like that. So symbolically, we have already used, we have a symbolical diagram as we work towards the circuit diagram. I mean, any tool we are using, we have an N channel MOSFET, P channel MOSFET that is available in that various symbolic form right now. Yeah. But one motivation issues like power dissipation, we've already discussed. Same here, but we found the scaling issues. If we go towards the lower technology node, we have a leakage power is the dominant factor over it. And that is due to the scaling scenario, and that is due to then we have a high drain voltage, we have some short channel effects arises. You can see that then the MOSFET subthreshold probe term is there. Basically, subthreshold is the, I mean, one of the degrade property of any device. So it should be as low as possible. But in the case of MOSFET, it is limited to 60 millivolt per decade. I mean, the minimum value of the gate voltage that is required to decade, increase the, or to decade the, to increment the current by 1 decade. So here 60 millivolt required in the case of MOSFET. So there is a limitation. Below this huge amount of volt we are required. So the scientist would like to suffer from that effect of channel, because ultimately once we have leakage issues and in that the device, ultimately we have an also. So in order to that, we are searching for some other devices, and we found some other motivation for towards the another tunneling devices or the graphene devices like that. So let us we discuss that how we have overcome that issue. So one is drain induced varial lowering like that. We have a hot electron. These are other sub channel effect due to the high drain voltage that we have. You can see we have calculate through that VD low minus VTH upon V supply. Like this, we can calculate. So in order to suppress the issue of the MOSFET, we go for TFET right now also. There is tunnel field effect transistor. So as the name indicates, the device, the charge carrier property is based on tunneling. That is the beauty of this tunneling device. That means it supports for the low power application very nicely. And here the substance will also be possible to go below 60 millivolt. I mean 0.35 or zero point 0.5 voltage is also sufficient. In order 0.05 we have incremented, your drain current suddenly increased like that. So subsystem slope is low, I mean low here in this kind of devices. We have some other devices also like graphene, we have MOS2, but only the problem is their controllability. But here we have a good electrostatic gate controllability over the channel right now, since we know that as per the energy band diagram, charge carrier will flow through the in the next second graph. You can see the on state. where the balance band of the source is directly charge carrier flow from balance band of the source towards conduction band of the channel right now. So in this way, your current will flow right now. Here. So here, in general, successful swing for the MOSFET, we have a 10 kT by Q like that. But it is, if we put at for the room temperature at 300 K, we found it's 60 millivolt per decade. We are not able to go below this. But for a device like tunnel FET, we are in position to go below it, maybe 50 millivolt, 40 millivolt. Some of the researchers proposed about even less than 30 millivolt also. So this is the beauty that low power, which the MOSFET failed, will be supported by the tunnel FETs. So few literature here, you can see here how the silicon T-FET and the other conventional MOSFETs will be able to there with their band-to-band tunneling phenomena, and they can work as a better device which overcome an issue faced by MOSFETs here. So they did their different optimization techniques. Suppose you can see here the overall channel length has been basically used by the some two different materials, and here like channel length and the tunneling length has been extended little bit. So this is the quantum tunneling process where band-to-band tunneling occurs between the source to channel, and the charge carrier will flow from to the balance band of the channel right. In another work here, if you see towards the device analog performances also right now, here just player, where you can see that in between source and channel, one high density layer has been inserted. You can see clearly in yellow color. So that in between source and channel, one high density layer is has been inserted, that is of high density and high doping. Due to this, which MOSFET, unlike MOSFET, fails to produce the high current, that we are in position to produce good current as well as transconductance as well as the frequency due to the optimized construction of this device. Next. In now, the beauty of this tunnel fit also applicable at the other devices for enabling IoT applications that has been brought by the emerging devices, circuits, in architecture. Here you can see just here that the material has been replaced by the gallium antimony, by the novelty based on material you can see by source gallium into GSB, and the drain and channel remains constant with indium arsenide like that. So what about the material research here? They have optimized and replaced the conventional silicon, germanium, and the silicon germanium compounds and the gallium arsenide by this gallium antimony. Since we know due to the optimized property of their O band gap, this compound material substitute and high significant for the more and more charge carriers to flow between the balance band to the conduction band, and in this way we are getting the low as possible up to 30 millivolt per decade success also, which is a great achievement we can say. Why? Because uh, low more will be the success or degrade the device behavior, but as low as possible that will be the always supported the SSD behavior. As I already discussed that the minimum gate voltage required to implement the drain current, that is your success also. So here we are in position to test that. So next we can see. Now we'll show for the software to implement the CMOS inverter designs. So that in order to have any basic gate implementation, logical gates, we have to implement using the CMOS technology. Any digital circuit parameters, if we have to implement through the CMOS technology, we have to produce the combination and the effective results and behavior, their performance for both P, MOS and NMOS like that. So similarly, conventionally, we consider the P substrate, I mean PMOS and NMOS But here we consider the P-TFET and N-TFET conductor. I mean that PMOS and NMOS is replaced by P type of tunnel FETs and the N type of tunnel FET like this. Similarly, we can also replace by the FinFETs.
sorry,
P type of FinFET and N FinFET. Here, this is one of the example from the experimental research data. Here you can see that has been implemented
submit
under
वगैरे कर, हाँ
130 nanometer of the 0.13
एखाद्याच नाही
micrometer
कोणता बंद
CMOS
करून
plus
टाकायचा
line
फक्त याचं चालू
guidelines
राहायचं,
under the
याचं चालू राहील
fabrication
फक्त.
experimental section for the implementation of CMOS technology under ultra low for IoT applications. Where you can see the VTC curve as voltage transfer characteristics, measured voltage here invert the same wafer of the standard CMOS platforms you find here right now, which has been defined between the output voltage with respect to the input voltage. So, what happened due to the beauty of the low power um, uh, capability of at the low threshold sync, we found a very low leakage under the T-flat of that CMOS inverter design with the help of this. And once we have the design, we have a comparatively data at the read write and the other leakage activities scanned by area. We found that the based on that we have various memory on 90 T-FAT, 90 T-FAT, SRAM design, CMOS. We found the various different other capabilities and the 90 T-FAT under that area of that found that 0.35 to 0.38 ampere I think not found change slide. Just a minute. Okay. Sorry. Okay. So, so here now, as now for the digital RAM application here, you can see practically from the device to low power device to circuit to model designs and from the model to the circuit parameter extraction. And based on the parameter extraction, we go for a memory or any circuit implementation, and then we go for the finally IoT circuit application here. So this is one of the example of implementation approach of device to circuit interface that once we basic elementary your device that already discussed, if you replace and if we have some low power optimization techniques, if already we have implemented over the device level, so we found the equivalent model. Model may be LUT, lookup table approach, based on the various parameter extractions and the multiple mix level simulation we can go. Second one is we have analytical modeling based on mathematical equations and to the MATLAB also we can go for the calibration. Second one approach is your Verilog A model. So Verilog A model, however, will also be designed only one spice file, but based on the parameter values like LUT model and all. So once we have the parameter that we have replaced it with the one file, where having the like from zero point 0 volt, zero point 0.02 step size, we have taken the train voltage extraction from the zero point 0.1, zero point 0.3, zero point 0.5 like up to that, zero point 0.2 volt to 2 volt like that. So in this way, if we are incremented through zero point 0.02 step size, we have multiple number of data parameter extractions. In that model, in a single file, we have called through the Verilog A spice file, and then we have a circuit implementation. Circuit, suppose we can draw the memory as RAM design, maybe 70, 60, 90. According to that, we have designed that static random access memory as RAM design here. And that SRAM now will be consist of your suppose the device, TFAT and other. So we have low power exactly we have. I mean the enable developed for that the remote areas where the device we would like no light device circuit flow. From there we can implement it. We can implement for the memory, any logical circuits that we can design from the device to circuit level. So this is all, however, the result variation we have, and one that we have designed just previous one. Just yes. So here we have a drain doping profile on double gate. Just a minute. Yes, yes. Now, so we already have the three structures like you can see here, where we have a low spacer width and we have a high spacer width. Three devices that we have comparatively compare and optimized here. Uh, and this green one, the cavity what you found here is basically the underlap structures. These are the underlap structures over the tunnel fed devices. Same we can draw, we can form over the MOSFET and FinFET also. So the underlap devices means that portion we have reduced somehow. So you can found that the gate length we have reduces due to the cavity formation from in the first structure, we have from both sides from source and drain. But in the second structure, we have both cavity structure also, I mean underlap structure, but with low spacers. Spacers basically act as the insulators over the source and drain we are right now. Why we these techniques we have applied only for getting the low leakage, and we have a high efficient device implementation here. Then the third one is we have low spacer bit. We have with drain side underlap only. We have no underlap structure over source side. In the third one, we can found. So we claim that the third one will found in the very best result for IoT applications and enabled. Why? Because it will support for a high power battery time with a low power efficiency. It designated for a very high performance over the other two devices. All the data what we have did considered is from the experimental only, calibrated and considered this for. But this third one that we have designed from novelty as a device from my side, as that we drain underlap structure with a low spacer width right now. So this C1 is will be the found with the best performance due to their high series resistance across drain channel. Since we have no underlap structure at drain side, so what happen means across source side. So we do not have a very high resistance because if we talk about the tunnel fed devices, we have a source drain across channel should be low resistance path because that current should be flow should be driving current on current, but across the drain channel the charge carrier flow dominate for the leakage current. So that's why we have made the underlap towards drain side and not towards source side in the structure, particular in the case 3 C, third structure. So that is how the AU, I mean asymmetrical underlap kind of thing we have. One side we have underlap, another side we do not have. So that's why we named it as asymmetrical. Other two structures have symmetrically because both have the same underlap structures. Third one will produces the low spacer bit with produces superior performance because across the drain channel there would be some underlap that produces the high series resistance, and due to high series resistance low tunneling is possible between so channel and drain, and that we actually want. Why? Because that will dominate for the leakage current. So in this way we have a low leakage current across drain side but high driving current across source channel junction, and that dominate for the leading current or on current, we can say driving current. So that is how we would have the kind of structure. So there, due to this structure comparisons, we found that red one will produces the very high result. You can found that is asymmetrical underlap, gate allowed low spacer bit. And because the other parameter remains the constant for all under 30 nanometer technology, or we can say point 0.3 micrometer here we have, and 7 nanometer radii with constant voltage of 1 volt at drain side with oxide thickness of 2 nanometer. So what we found that the AU with low spacer bit produces a high electric field across source channel. Also, you can find the red color that indicates the specifically indicates the high source channel electric field that produces the high driving current. Right, that will be best suited for the low channel. Right now we will implement that particular TFET in the inverter CMOS design that we already discussed. Now with the help of the devices, stages and their results you can found. Once we replace the MOSFET inverter or the CMOS conventional structure with TFET inverter. TFET already we know that consists of P channel and N channel, both that form the proposed device for energy harvesting and IoT applications. Here you can form. So once the P channel and N channel both we have formed and replaced by the TFET right now we can say. So here you can found we have also implemented one circuit that is cross coupled voltage double circuit. In my software like TCAD and the circuit combination. We have implemented this. The model we have called this the tunnel fit TFET model. So the device MOSFET we have replaced by the TFET and we have implemented this circuit. This gate all around kind of structure TFET we have considered. Gate around is actually that gate should be wrapped across all side of the channel and it should be I mean, wrapped and charge carrier will flow across all the four sides of the channel, right? So that is how we have cross couple voltage doubler circuit with clock switching platforms right now. So now come to the basic logic gates and combinations we have. So we know very well the basic gate combination log gates using that either maybe basic AND gate or gate NOR gate their implementation. But using the PMOS, CMOS and how that has been implemented with the help of in the Verilog structures for the PMOS, CMOS designs like this we have. So we will see in our coming slide how we will write and form that implementations. Hmm. Hmm. Just a minute. Let me see. So here we found that the pull-up network and the pull-down network, where the pull-up network is has been implemented by the PMOS, while the NMOS is implemented the pull-down network. So with the help of these both structures, we found the parallel and serial combinations in the inverter circuit. Here CMOS implementation by connecting the input together and where we found here how can we implement the basic circuit with the help of the devices and their coding and implementation in Verilog. Next, please. So here now we see some basic implementation of the combinational circuits like multiplexer, adders, sequencer circuits, and two complex one. We have two ratio one marks like that, and the decoder that converts binary input to one output, or maybe the two to four or 4 to 8 like that. Similarly, we have a half adder and full adder combination over their sum and carry implementation house that we will see gets to a simple processor. Next one. Yeah. So before implementing with the Verilog implementing coding, we let us also discuss the basic standard cells and the steps while blocking and planning like that, while building and assembling the floor, where we have a floor planning, placement, and we have somehow the routing right now. All these are the important parameters while implementing the any circuit before tap out, we can say. Why? Because floor planning, uh, like that, we have planned for suppose in our houses also before getting any implementation, we have an architecture how to be placed the our devices as per their law, so that a crucial step in the VLSI physical design flow, where the layout of different functional blocks, ALU, memory is planned on the silicon chip area before any detailed placement and routing, right? So in deciding where each block will sit on the chip, right? Shape and size of the chip, positions, placement of input outputs, power and ground, like that, all steps we have implemented with import netlist. And right now we can say core and die area placement, macro placement, pin placement, power planning, right? Similarly, if we go towards the placement, how the standard set get placed inside the core boundary. So we can say it depends on the fact that how the placement is done and have large runtime to perform the steps. So include the important steps in which the EDA tools perform to complete that placement. So it is used to placing the standard cell inside the core boundary in an optimal location, and also support to place the standard cell in such a way that the design should have minimum and the base timing. It also support to provide various
तुम्ही फोन
commands
चालू
and
केल्यावर
users like now.
रेकॉर्डिंग तुम्ही चालू
So
केली
we can say the placement
म्हणजे प्रेझेंटेशन
not only the standard cell present in the synthesized netlist, but also used to place many physical cells, adds, buffers, we can inverters as per the requirement, like this we can do. So now we have important time during the foundry requirements. Now we will go towards the routing that connects all signals. So routing, as we already know that the process physically connecting all the placed components, states, micros, like that on a chip using metal wires according to the netlist. Similarly, we can have the E cell to be located and nets are connected where no circuits or open circuit design, timing, area, and power constraints can be have designed. Under the routing, we have a global routing, detailed routing. Somehow we have a routing layers, power and signal routing, like that. So according to the implementation we have. Now we have a DRC. Under verification, DRC plays an important role that used in electronic design. That for integrated circuits, somehow we have a PCB boards to verify that a design meets the manufacturing and performance constraints somehow. So it ensures the design that will not result in defects, basically, or failure while checking parameters, maybe the trace bit clearances, and spacing against the set of predefined rules. So under DRC, we have a DRC verification of the physical layout, specific capabilities. Somehow at the time we can also compare and the design's layout against the set of rules provided by the foundry. Then maybe sometime violation reports also can be overchecked, and we have a traces and layer spacing while component placements between different components and on a board while we have can enclosures like that. So it all these we have about the DRC. Now we'll go for the LVS, that is layout versus schematic. Again, it is one of the important parameter while implementing any digital circuit or the log also we can have as well. Now we'll go for the layout. that is used in VLSI design to ensure the physical layout of a circuit matches its schematic designs. So LVS, we can found why it is important because any two nets accidentally or wrongly connected or missing any extra that we have checked and properly we have connected and matching the devices types using correct all devices maybe transistor register their connections that is how LVS is very important. Layout versus schematic, we can check. So whether layout is as per schematic design or not, finally, that we have optimized and we can verify through that LVS. Now we'll come to the timing analysis. Timing analysis in a VLSI basically to ensure a digital circuit meets whether it's speed requirements or not like that. But in particular, all signals arrive at their destination allocated time. That is more important. So the most important methodology under the timing analysis is STA, that is static timing analysis, where the industry nowadays require is STA experts and their job so much. So that all timing path for violation like setup, hold times, without needed any extra test vectors, including calculating delay through logical circuits, somehow for both setup and hold violations, to guarantee the chip operates correctly at a target frequency. All these are very important under this. Somehow we can say in short, it exclusively check all possible path to identify violations like setup and hold timings. Now next letters we have Verilog. So you can see somehow the Verilog code. Simply here we have. Firstly, if we discuss about the Verilog implementation, it's a hardware description language, HDL. Why we have used this language? Because with the help of this code, we have a feel how the hardware devices have been connected using the wiring and the as well as their logical decisions that we can design using the coding. So that is how it is known as value. It's a pure hardware description language, HDL, we can say. So how to write a sample to input AND gate? Here you can see, and now we will design here two input AND gate where we have first is we have a module declaration. You can see here module we have declared where the modular name and a list ports where you can see like A and B we have given two inputs. While we have a port directions, that port directions declare whether input or output like this we have. Then we'll go for the implementation part. Implementation where the behavioral like output is driven, assigned, and the decision get primitive, and somehow we have a structural instances like that. Here we given always at the rate a comma b like this. So the decision is like that always for getting the output y a should be in multiplication with b. That implementation we have deducted. I mean we have incorporated here that will using the AND module as a syntax. We have time scale and test bench. We have completed. Test bench basically a separate module that drives input and checks output. And then finally, we have a simulation and synthesizer. So one example also we can see by writing here practically, if people can see. And if you want, then anytime you can go for the Verilog. It's a very interesting and language also. So let me found mm, just a minute. Suppose here we will go for gate structure. So you can see here just a minute.
माइक बंद
Okay. So here we have XOR kind of fitting. You can see directly we have opened the process here very low way, the xylene. Now we have given the two inputs A and B, which you can give about the and analysis for the output waveforms. Once after that simulation, we have the output waveforms under the XOR gate. So XOR, we know very well the decisions like that A bar B plus A bar or however one if both remains both inputs are zero or the both inputs are one, then only we are getting somehow. So values. So here we have given two input here XOR. So let me open the wire bench code. Good. Yes. So how to make a Verilog test bench here? We can analyze where the new project add or get something we have implemented here. The two values A, B, while the wiring and the output wiring will be replaced by the Y only. Then the decision has been made. We have 0. Then if A is 0 and B is 1, then we have this. So ohm binaries we have made right now. Here the values that we have given. So all the possible input combinations is given with that. You can see here. Now we'll go for another example just now. For that, let us see the BEF forms. So this is the BEF form here, where you found the value A is given 1, B is given 1, then output we are getting 0 like this. So the same values or we are getting the output 0 here that can be observed with the help of BEF forms. For the different values, we are getting 1 like this. As per the principle of XOR, you can see here with that in the input A and B, whenever both are value 1, 1, we are getting 0, but we are getting 0, 0. If we are giving the A is 0, B is 0, then we are getting 1. The same as we normal. Okay, the next, let us see the next example we have. So verification, under that we have somehow the state possibility state explanation right now. So here I changed the slide. Is it visible now? Slides. So let us we open the another example. So we go for the verification ball that refers to the growing difficulty of verifying increasingly complex chip designs. Somehow there were described the design tools and methodology that can handle somehow the complexity. We have And as chip becomes more complex, I mean, the process of transistor verifying take suppose much more time than the designing right now. So extendedly, we can say the functional communication blocks, which need separate system level verification. Here, suppose we have a limited simulation speed that can't keep up with the number of test cases required. So here,
The silicon
we will
wafer
go
fabrication,
to the
verification
silicon
with
wafer.
the wafers. Somehow we have so many implementations. I mean,
Devans Joshi.
that increased transistor density, somehow the power density and this the dissipation issues, heat dissipation issues, then the end of Dinard scaling, while leakage current increases. All these are the adverse effects over it. So dynamic voltage and frequency scaling we have with power gating, clock gating, all these are the techniques that we can improve or we can implement to mitigate the power loss. So clock gating, near threshold gating, somehow we have improved thermal management, architectural innovations. Suppose we have used the techniques exactly. Now we have a VLSI physical wall under that. So the physical wall challenges basically the limitations and difficulties in physically realizing, fabricating the smaller and faster chips. So we can say it is one of the main barriers with Moore's law. Since there are some challenges, why this physical wall attempt due to the quantum effects, power density, somehow interconnect density and the delay, leakage currents, and variability we have. Due to this atomic variation, the rising cost are the challenge over it. We will have. So we'll go for that economic issues. And here we found that at least we required the $500 million design cost for 3 nanometer chips. So how much the whose loss and would be the economic issue? That is the current VLSI challenges we have. So somehow as per the VLSI challenges, presently we have in the form of either verification wall, power wall, or the physical wall. Ultimately they goes towards the economic issues. But somehow we will try to overcome it by the various scaling, I mean the various techniques, still doing technology and right now. Yeah. Before this, one more example we have.
Just a minute. Let me open and we show you the bugs that we tried to implement. Yes. So in a Verilog here, again, we would like to implement two input maps right now in the form of D0, D1, and then we will begin with the output Y right now. So first of all, we know that we have to select a set of two inputs in generally it's a basic principle of the multiplexer to get to the two output Y depending on a select signal S1. We have because in both the cases we have A and B right now. So here you found the two D0, D1 like that in the amplifier. With the step-by-step design approach, you found two data inputs A and B select here one and the output Y. So that's why we consider D0, D1 and S here. While the output we can recognize through Y. Now the decision and synthesize here friendly we will go for like that here either D0 or D1 or S. Out of all these three values we have to select. So we will go for synthesis friendly to avoid latches, use full sensitivity or continuous assignment, and go with the test bench. That basically drives this combination and check for all three possibilities. So suppose always if S, then Y is basically D1, and else it will give the D0. So selection is based on the value, whether we have considered the S, Y, and like this only. And we'll go for the AND module selection like this. This is where constitute very low. Here we have. We can see for decoder like this. Just a minute. Let me see. So decoder, we know that for a n bit binary input we have now, and using the Verilog we will implement here. So we consider here 3 to 8 decoder right now. So from that output values, we know for the 3 to 8 decoder we consider 0 to 7. Or in the binary we have like 0001010011 like that up to triple one that significant for the 7. So 0 to 7 number of values we have 8 here. Now in input we have given and syntax by the I to 0, and all these value default and that syntax and end by the end case and end modules right now. So what happened in this way, each output line is an AND of all input bits and their implementation. So we found that Verilog were the most common and clean method. Under this, we can implement not only for 3 to 8, it may be for high value 4 to 16, and like that before to do the basic. And we can implement any hardware descriptions. We can implement and test here. So in the Vivado open that we can create a new project and go with the RTL project, a design source and simulation, and can go for the simulation file, run behavioral section, and application file. So as an hardware and open source, anyone can do this. We do not require any kind of license also. Officially, it will be allowed because it's open source for that. So we can't say it would be some crack version or something we have to struggle for that. No, it's open source and would be officially available for all student faculty as well. So these are the small implementation. Now discuss about the basic VLSI flow from that. So VLSI design flow just now. So we know that it's a systematic and integrated circuit basically. So with the help of these HDLs, we can go for the systematic process of designing a IC chip, and up to the GDS2 level, we can implement using any professional circuit tool like Cadence, Synopsys, mixed level simulation, like that. So a core component, we found that under this, we have to go with specification for any VLSI implementation, where it would be the starting point implement right now, where we can have the chip performance, functionality, power, and area requirements. According to this, so power and area both are the very important terms here, where we can go with the testing and specification. When we'll go get the specification requirement for the processor and the frequency as well, then we'll go for the architectural design, where we have to take the decision how the functionality will be implemented at a high level, choose the number of ALUs and the memory hierarchy, like that pipeline stages, etc. That we will go under this. And also we have an module of output where we can show major components interaction. So when the architectural design successfully completed, we have an RTL implementation, that is registered level. Since in the RTL designs, we have hardware description code in Verilog or VHDL, where we describe the data flow between register using combinational and sequential logic. So this RTL register transfer level synthesize define the values here, and where we can go for the tools
Google Calendar
Xilinx,
वरती ना
Vivado,
मीटिंग शेड्यूल
Cadence,
केल्याच फायदा आहे
Synopsys,
तिथं लगेच दिसतं
any
कोणतं चालू
after
डे
this.
टू सेशन वगैरे कोणतं
Then we will
सेशन
go
झालं
for
सगळं
a
दिसतं
and more important thing, that is functional verification. Functional verification, where we have
आईले आपल्याला
the
काही माहिती नव्हतं
RTL designs work logically as intended and
पहिलं
describe the
लय
run test
झालं रे
bench
पहिलं लय भारी
simulations
होतं
or even
इनॉग्रेशन
formal
व्हायला पाहिजे
verifications.
इनॉग्रेशन आपण
Then
झालं लय
go for
कामाला
the
असतं माहिती का
tools, model sim, cadence,
तीन
SIP,
अरे
synopsis,
डाउनलोड
etc.
म्हणून काढतील का
Where synthesis and after
आपण
the
सांग ना
successfully
सिकिंदवाला ते
functional
कर म्हणते मी
verification,
डाउनलोड
we
करते
go for the synthesis
बरं नेमकं
designs.
तिथं असं झाला
Where the
रेकॉर्ड
synthesis
करायचं बटन
here
दाबायचं राहून
convert
गेलं
the RTL code Verilog into the gate level netlist using the standard cells that maps your
कधी
logic
सरस्वती
into
वंदनापासून
NAND,
चालू केलं
NOR,
होतं
flip-flops, etc. based on standard cell libraries we have. So RTL to synthesis that map your logic, logical gate, any gate circuits based on the standard cell libraries and to get level netlist. That would be the important implementation of under the synthesis right now. Then we will have a synopsis design compiler, as we already know, Linux and Xilinx right now. Then we'll go for the design for test, DFT. As the we know that any extra circuitry like scan chains to make post fabrication testing helps in finding faults in the manufactured chips. So the any supporting commercial tool maybe Synopsys, compiler, mentor transit, etc. will help for the design for test, DFT module and their implementations. Now, the specific tools and the Synopsys compiler like Manta, Tezent, etc., that we will go. And now we would like to implement for the floor planning after the successful DFT techniques we have. So that will go for the floor plannings. Plannings, as we know, that placement areas where the each blocks on the chip and input output pads, power grids, and block boundaries that has been defined, and will have introduced over the input output pads, power grids, and the block boundary. Then finally, we have reduced the routing complexity basically with the help of floor planning. And here also for this we can use the tool like Synopsys IC compiler, Cadence Innovus, etc. The commercially tool we can use here. Then we have placement. Place the standard cells such as gates, flip-flop, etc. inside any assigned areas, the specific chip area that significant for the placement under that after the floor planning, where we minimize the violence and delay, and accordingly we will go for the placement of the values. Now this in continuation will have clock tree synthesis where we distribute the clock signal evenly to all flip-flops with minimum skew values. Where balanced clock distribution for synchronous operation we found, and we found that to distribute the clock signal evenly to all flip-flops with minimum skew values, we can have balanced clock distribution under the synchronous operation. Then we will go for the routing where it connect all the placement cells using metallic interconnects. So routing where install all NAT connections and physically wire from the physical layout with the help of the routing we can say. So these are the steps where we found after this routing. Then we'll go for the physical verification. So physical verification, as of now, already know that after layout, we have to perform few checks. We can say the verifications under that. That's why it's named as physical verification. Basically, verification we have to do in the form of DRC, maybe design rule check, LBS, layout versus schematic, or sometimes we can go for ERC, I mean, ensure no charge damage issues like that. So we have a ERC, DRC, LVS like that we can go. Here also, this physical verification can well implemented using Cadence PBAs, and one more tool like Manter Caliber can support it for this. Then we'll go for the timing verifications. Right now, the static timing analysis that will help to verify setup and hold times that would be satisfied across all paths right now. So Synopsys prime time and cadence will the primary, I mean the two parts of this STA timing analysis, and then will after this timing analysis will finally go for the GDS2 generation. So GDS2 is basically the end file we can say foundry. Now our foundry ready for chip fabrication. So we can say the file is ready. So for the foundry for chip fabrication we can say. So actually the final physical layout is basically known as the GDS2 file we have. So under this we have an output and fabrication that is used by semiconductor foundries like in our India we have SCL. However, it supports for 180 nanometer, but we have at least we have that in Chandigarh SCL Mohali Silicon Conductor Laboratory we have. But generally in EVA only one place, but in TSMC, Intel, Global Foundries, all have in their respective foreign head offices. They have their foundries to create the physical chip on a silicon wafer right now. After that silicon chip fabrication, we will go for the testing and packaging right now, where the after fact fabrication the chip is tested on hardware, testers, and packaged, and that will help for the functional and timing testing ensure with the proper operation right now. So somehow we can say one circuit cadence. Let us any. I will try to open any tool, any circuit tool maybe for that. Just a minute. So I will show you. So the flow is like that. Basically, I repeat it. From specification to architecture, then RTL, then we will go for functional, like this. So I will try to show you.
सही आवाज बंद करनी चाहिए फोन करवाई लगा
So one of the circuit I download just to show from the cadence actually. So since we have a limited time, otherwise we can have a live demonstration with the cadence, uh, so that we found how can we implement. So this is the basic cadence circuit for the XOR. This is the combination of PMOS and NMOS we have drawn and made. So with the help of PMOS and all, we have implemented here the XOR circuit where the output represent for basically A bar B plus B bar like this, and the same input that we have output somehow 0, and for the different inputs we have 1. Same we have implemented here. Earlier we see the case in the Verilog, but here we have seen with the help of Cadence. Cadence is one of the commercial circuit tool where we do not require any coding. Directly using CMOS we can implement the combination of PMOS and NMOS. So that is how here we do not require any coding. But after this directly we can go for the schematic circuit that circuit is in front of you. After this we'll go for the waveforms. Once for the waveforms, successful waveform, we can directly go for the RTL design and functional verification. Once we go for the Verilog, after this we can go for functional verification, synthesis, and then we'll go for the Verilog RTL that we already discussed. RTL designs that again have been followed by functional verification, then synthesis in the form of netlist, that followed by EFT insertion and floor planning. Floor planning is again implemented by placement, clock tree, routing, and GDS2. GDS2 file that we have already discussed will be here, where it represent and the implemented here like this. And then we'll go for that graphic data system here. So once the graphic data system, I mean the GDS2, to represent the layout of an integrated circuits, and after that GDS2 directly will go for the foundry. So from the basic circuit of XOR also, I mean to encourage you that you people can go for the layout verification and for the chip design. Finally, for the tape out fab, I mean implementation. So you can go if you have nowadays we have EDA tools and encouragement by the C2S scheme and the packages by the government of India. So it is no cost. I mean, without any cost, you people can implement and go for the chip application. Their purpose is that with the help of these EDA tools, the fabrication also fabricated by the cost has been effectively by our government of India, SCL Mohali. And initially they can implement it under 180 nanometer, but later on for just prototype, but later on it will go for final implementation that will manufacturing and all. So the chip is sent for tap out that contains all geometrical shapings. So that's why once you design this graphical data system GDS, then we will have the final GDS2 file and you people can go for the implementation on the circuit like this for tape out. So that is how I open this cadence system. I can even share with the sir. There is some link for the cadence that if you want, then you people can use. I will share it with
Okay, record sir.
Bhagwan sir,
Recording
whatever
record.
it is,
Sangat daw.
so that the
He sangat
practice
daw close
purposes
book.
can implement it. Basic, very basic, basic logical circuit like that. We have XOR, encoders, multiplex. I mean, 2 by 4, 4 by 8,
W sir.
like this. And then you can go for some medium level circuit also like SRAM design, static random access memory. Here we have not discussed, but SRAM, you know well, it's not quite complicated, but like a CMOS inverter design, we can design 60 SRAM, 90, 70. T means basically 7 transistor or 6 transistor or the 9 transistor like this. Like this, we have it. Read write operations you can achieve. And now in India, 2 nanometer technology is already in research in companies under Micron, Infochips, Qualcomm, etc. So now in coming days, it would be a huge demand for expert engineers. Means there would be a job, but the skilled person is not available like this. The thing is like that. So that's why I encourage, means I request all of you to encourage your student if they are. So the student can go with this area of digital or analog VLSI, go with some like Verilog, cadence, and synopsis with very basic circuit implementation. Once they got, definitely would be supported, encouraged nowadays by the government schemes, and they get placed in VLSI. Thank you, thank you. That's any doubt?
Thank you so much, sir. Dear participants, if you have any query or doubt, you may ask to Dr. Ankur Beohar, sir.
Hello.
Uh, Dear participants, please, if you have any query or doubt, you may ask to Dr. Ankur, sir, please. Or you may type in chat box, or you can mail us on bhagwan.sonone at srimahir.org. So, sir, okay, then we can conclude this session. I think
Yeah, yeah.
the
Otherwise,
participants.
I can share the email ID also if you require.
Yes,
And
sir. Yes, sir. I think there
anything
is no
people.
participants who have any doubt or queries. So, thank you so much,
Okay.
sir, for such an insightful and informative session on future of VLSI, digital design and digital twin technology. Your talk has truly helped us understand the evolving role of VLSI and simulation technologies in shaping Industry 4.0 applications. On behalf of organizing team and all participants, I express our sincere gratitude for sharing your valuable knowledge, research experiences, and industry insights with us today. Thank you once again, sir, for taking the time to join our FDB and enriching us with your expertise. Thank you, sir.
Yeah, yeah. Thank you, sir, for the opportunity. I would again thanks to Sambhaji sir, also and other team members to be here. Thank you, sir.
Welcome.
Okay, sir. So shall I leave now, sir? Yeah.
Yes, sir. Yes, sir. Yes, sir.
Okay, sir.
Dear participants, dear participants, please fill up the feedback form and complete the assignment. Which the link will be shared on WhatsApp group. The feedback form and assignment are mandatory for the purpose of certification. So please fill the feedback and complete the assignment. And next session will be tomorrow at 11 a.m. So please be connected at 11 a.m. See you soon.